I'm Rajendra Kumar Patel, PGT Chemistry, GNV Golaghat, Assam. How are you, students? I hope you will be fine at your home. So, students, today we will discuss about Kohlrausch Law and its applications, and also we will try to solve some numericals. This video is for class 12, unit number 3, that is electrochemistry. So, let's start, students. You know, the Kohlrausch law, it is related to the limiting molar conductivity of an electrolyte. So first let's see what is limiting molar conductivity. The conductance of an electrolyte at infinite dilution, and which conductance? It is molar conductance. So simply we can say the molar conductance at infinite dilution is known as limiting molar conductivity. It means when the ions they are 100% free, when the ions are 100% free to move anywhere, then their conductance it is at maximum rate. Okay, so simply we can say the ions they are conducting at their level best. So what is limiting molar conductivity? The molar conductance of an electrolyte at infinite dilution. So the Kohlrausch law, it is related to limiting molar conductivity. How? So before seeing the applications and the numerical form of this Kohlrausch law, let's see first the definition. So according to the definition of Kohlrausch law, the limiting molar conductivity of an electrolyte is equal to the sum of limiting molar conductivities of cations and anions respectively. It means for an electrolyte, if we want to calculate the limiting molar conductivity, then simply we can find by adding the conductivities of its anions and cations at infinite dilution. So the mathematical expression is lambda naught m. M means this is an electrolyte. It is equal to lambda naught cation plus lambda naught anion, where x and y, you can see these x and y are the number of cations and anions respectively. For example, if we see the example of sodium chloride, then for sodium chloride NaCl, the Kohlrausch law can be written as lambda naught NaCl, it is equal to lambda naught Na plus and lambda naught Cl minus. Here you can see clearly that if you dissolve NaCl into water, it will generate one sodium ion and one chloride ion. So the value of x and y are 1. Let's take another example, that is aluminium sulfate. So for aluminium sulfate, the Kohlrausch law can be written as 2 lambda naught Al3 plus and 3 lambda naught SO4 2 minus. Because aluminium sulfate, when we dissolve it into water, it generates aluminium ion and sulfate ions. So simply to find the value of x and y, we will see only the number of atoms. Okay, see how after aluminium it is 2, Al2. In this formula you can see Al2. 2 means number of aluminium is 2 and number of sulfate SO4, number of sulfate is 3. So x and y we can easily find. So let's see, students, the numericals which is related to Kohlrausch law. So in this numerical, in your textbook you can see the example 3.7, that is calculate lambda naught for calcium chloride and magnesium sulfate. So for this, the values of the limiting molar conductivities of calcium, chloride, magnesium and sulfate, these are given in your question. Okay, so this will be the question, and like that the question will be in your exam. So first we will solve, we will calculate limiting molar conductivity for calcium chloride. So for calcium chloride we can write the Kohlrausch law as lambda naught Ca2 plus 2 lambda naught Cl minus, because number of calcium is 1, number of chloride ions is 2. Here's simple way. Now we will put the values of limiting molar conductivities of calcium and chlorides, then we will solve it, the value will be there. And no need to remember the unit, because unit is already given in question. So this is the first part. Now limiting molar conductivity for magnesium sulfate. So for magnesium sulfate we can write the Kohlrausch law as lambda naught Mg2 plus lambda naught SO4 2 minus. Simple, we'll put the value of cations and anions, then solve it, you will find easily the value of limiting molar conductivity of magnesium sulfate. So it's a simple way. Simply we have to find the number of cations and anions, and after that multiply with the values of limiting molar conductivities of cations and anions. Simple. Now we'll see the application of Kohlrausch law. So the first application is to calculate the limiting molar conductivity of a weak electrolyte. So students, as we know, strong electrolytes they ionize 100% into ions. Means if you take 100 moles of NaCl, sodium chloride, then when we dissolve in water, it will generate 100 moles of Na plus and 100 moles of Cl minus. So this is the case for a strong electrolyte. So for a strong electrolyte, we can use Kohlrausch law directly. But for weak electrolytes, since weak electrolytes they are not 100% ionizable, so how will we use? So to explain this application, I am taking here example of acetic acid. You know, acetic acid, it's a weak acid, so it doesn't ionize completely into ions. So the ions which are generated by dissolution of this acetic acid are acetate and H plus. So simply we can write the limiting molar conductivity of acetic acid as this one. So now if in a question, if we don't know the values of acetate and hydrogen, then if in a question the values of limiting molar conductivities of 3 different electrolytes, strong electrolytes are given, then how can we use? It means by using the limiting molar conductivities of 3 different electrolytes, these are strong electrolytes, so by using their values we can calculate the limiting molar conductivity for weak electrolyte. How? So see, here is a simple concept of maths, and that concept is, if you add the same value in an equation and minus the same value, then there will be no effect. For example, here you can see the acetate ion CH3CO minus H plus, these are same. I am adding here Na plus and subtracting Na minus. So simply from mathematics it is clear that if here, since the signs are opposite, so these can be cancelled. Like that, chlorides, they will be cancelled. So there is no effect on the value of the equation. So students, now we can write this. In next step we will just rearrange the ions. Rearranging means, here see, only we have written what? We have written here we have reshuffle the ions. For with acetic acid I am writing sodium, with H plus I am writing Cl, and like that. So here after rearranging, now what I am going to do is simple, and the thing is we will combine these two, then these two, and after that these two. So when you do this, okay, then you will find that by combining acetate and sodium we get sodium acetate. By combining hydrogen and chloride we get HCl and sodium and chloride NaCl. And also the sign are very, very important, since the sodium and acetate both have positive signs, so they will be positive. Since H and Cl, you can see in red color the positive signs, so they will be added, and Na and Cl, they have minus sign, so they will be added to form NaCl. So another example, it is for the application to calculate the limiting molar conductivities of weak electrolyte. So from this example you will simply find how the question will be solved. So here, if 3 electrolytes, these are strong electrolytes, these are ammonium chloride, sodium chloride and sodium hydroxides are given, then how we will use their values to find the value for ammonium hydroxide, that is NH4OH. So simple thing. See, where is NH4 in 3 electrolytes? So it is in NH4Cl. Where is OH? It is in NaOH. So we will add the values of ammonium chloride and sodium hydroxide, and then last one is sodium chloride. We will subtract it. So in this way we can find the value of NH4OH. So students, let's see some activities, numericals. That is 3.8 in our textbook. The limiting molar conductivity for NaCl, HCl and NaAC. NaAC means sodium acetate. This one is a strong electrolyte. Are given. So calculate lambda naught for acetic acid. So simply see how will we use the three values. So yeah, first write the given things. These things are okay like this. So now here see, we have to calculate the lambda naught for HAC. The H in HAC, see where is H? So H is in HCl. Where is AC? AC is in NaC. So we will add the value of HCl and NaC. Okay, and from that value we will minus NaCl, value of NaCl. So what will be the equation? HCl plus NaC minus NaCl. So we will write this equation. Lambda naught HAC is equal to lambda naught HCl plus lambda naught NaC minus lambda naught NaCl. Put the values and then you will find the answer. And the units are given in question. So this is the application. Okay, numerical part. Now see. Now we will see the next applications. Second application number 2, to calculate the degree of dissociation of weak electrolyte. Degree of dissociation means if we take 100 moles of an electrolyte, then out of 100 moles, how many moles of electrolyte are dissociating into ions? If 100 moles are dissociated, then it is the degree of ionization is 1, means 100% it is ionizable. So here we will see how many numbers of moles are actually ionizing. So see, how can we calculate? So to calculate the degree of dissociation, the formula is alpha. This is the degree of dissociation. It is equal to lambda Cm. This one is not, it's due to some technical. This one is what? This one is like this. Lambda C and this one is M. So lambda Cm divided by lambda naught M. It means this one is what? This one is lambda naught and this one is M. This one is the molar conductivity at infinite dilution and this one is molar conductivity at concentration given in question. Concentration means it may be 1 mole, 2 mole, 0.5 mole, 0.1 mole. So any concentration we can take. So we will find the values of molar conductivities as C concentration and the limiting molar conductivities. So after writing these, what will we do? We will simple next. So from Kohlrausch law we know that the lambda naught M, it is equal to the sum of limiting molar conductivities of anions and cations. Okay, so in this way we will find the value of degree of dissociation. The third application is to calculate dissociation constant. This dissociation constant is Ka. Sometimes it is written as K. So this Ka, it is equal to C into alpha square divided by 1 minus alpha, where C is a concentration and alpha is a degree of dissociation. We can calculate from second application. Okay, so to understand these two applications, we will try to solve a numerical, and the numerical is example 3.9. The conductivity of 0.01 0.001028 mole per liter acetic acid is 4.95 into 10 power minus 5 Siemens centimeter inverse. Calculate its dissociation constant if lambda naught m for acetic acid is 390.5 Siemens centimeter square mole inverse. So students, here what are given? Conductivity is given and limiting molar conductivity is given, concentration is given. So first we will calculate the molar conductivity. So the formula of molar conductivity is kappa into 1000 divided by C, where kappa is conductivity and C is concentration. So put the value of kappa, that is 4.95 into 10 power minus 5 Siemens centimeter inverse into 1000 divided by C, concentration, this one is 0.001028 mole per liter. Okay, so if you solve this, you will find the value 48.15 Siemens centimeter square mole inverse. This is the value of molar conductivity. Okay, now we will calculate the degree of dissociation. So how degree of dissociation? So to calculate the degree of dissociation, alpha, that is equal to molar conductivity divided by limiting molar conductivity. Molar conductivity, okay, we have calculated molar conductivity as 48 point, this one is 48.15 divided by 390.5, it is equal to 0.1233. This is the degree of dissociation. Now by using the degree of dissociation, we will calculate the dissociation constant. So the formula of dissociation constant is C into alpha square divided by 1 minus alpha. So now the concentration given in question is this one, okay, into alpha. So value of alpha we have calculated 0.1233 square divided by 1 minus value of alpha. So you solve this and you will find the answer 1.78 into 10 to the power minus 5 mole per liter. So in this way we will find the value of molar conductivity, degree of dissociation and dissociation constant. Okay, so now that's all for today's lecture. Thank you very much. If you have some problem, you can ask to my personal WhatsApp number. Thank you.